Yes.
Okay.
Yes.
So the next speaker is Anirban Datta from Benares Hindu University.
Okay, so first of all, I would like to thank the organizer for giving me the opportunity to present my work here. Sorry, what is this? Okay, so this work has been done in collaboration with my colleague Devanand, and then this is an extension of the work done in this manuscript. So in this manuscript, they have done the work in terms of Hubbard X operator. In our case, we have done the calculation in terms of fermionic language. So we can see, due to the fermionic language, we can see explicitly what are the process that is happening in the system, and due to the fermionic language, the calculations are slightly difficult. And we have used a different method, and that method is well explained in this review article, which is by Professor Kuczynski. So now let me start with in our work. So we have developed a semi-analytical framework formulated in the canonical fermion language. Okay, and this formalism can be applied to strongly correlated systems. Yes, am I audible?
There's some interference happening.
Is it?
Yeah. Okay. Good.
Okay. Okay. So is it clear now?
Yeah.
Okay. Okay, so we have developed a semi-analytical formalism formulated in terms of canonical fermion language, and we can apply that to a class of problems. So for example, let us consider we have a Hamiltonian H, where H naught is the free part of the Hamiltonian and V is the interaction part, and we want to solve this Hamiltonian in the strong correlation limit in such a way that lambda is of the order of 1. Okay, so no standard perturbation theory will work, so we have to develop a new formalism for that. So I will come to that. So for that, so this solution is not exact, so it's an approximate solution. And second thing is that it's a non-perturbative method. Okay, so since no perturbation theory is worked, so it's a non-perturbative method. And second is that we have used the equation of motion formalism. And then due to the since our calculations in terms of fermionic language, we can identify what are the relevant scattering processes. Okay? So that's the idea. So we have applied only to one phase of the material, so which is basically strange metallic phase of the cuprate superconductor. And the question I just want to ask, so can a microscopic lattice Hamiltonian explain the strange metal phase? So we have not done the calculation for other phases, so we believe that it can be extended, but so we, in this presentation, we will only talk about the strange metal phase. Okay, so this is the typical phase diagram of cuprate superconductor. So at zero doping or at half filling, so due to the strong Coulomb repulsive interaction, the charge degrees of freedom are frozen. So we have an inherently insulator phase, but the spins can fluctuate because of the second order fluctuations, and then at high temperature we have the disorder paramagnetic phase, and if you lower the temperature below certain temperature we have the antiferromagnetic order. Okay, so and the ground state is given by the nil state. Now if I just increase the doping, the antiferromagnetic order just gets destroyed and a superconducting dome emerge. At certain optimal doping we have the highest TC, and if we go across this direction, across the temperature, we have the normal metallic phase, we have the metallic phase, and this metallic phase has been broadly classified by three regions. So at high doping we have the normal Landau Fermi liquid phase. Here we have the strange metal phase, which I will come later, and then there is a pseudo-Guff phase at a very low doping, which is characterized by depleted density of state close to the Fermi surface. So we are mainly interested in the strange metal phase, so we will come to that. So we start. This strange metal has important property that it shows the linear temperature differences in the resistivity data. So usually if we apply, so we know that from the Landau Fermi liquid theory, the resistivity scales as T square. Okay, so but here in case of strange metal it shows the linear temperature dependence. Moreover, this linear temperature dependence is maintained beyond MIR limit. MIR limit is certain limit where the mean free path of the electron is comparable with the Fermi wavelength. That in this limit usually the standard Drude-Boltzmann theory of transport stops working, and then so for normal metal, usually the resistivity saturates beyond this MIR limit. On the other hand, for cuprate superconductors, so basically in the strange metal phase, the linear resistivity is maintained beyond the MIR limit. Okay, so to understand this, we start from the single band Hubbard model, because the simplest model we can construct for cuprate lattice structure is the single band Hubbard model, where T is the hopping strength, and then we have the interaction U, which is on-site interaction. It's given by Ni up and Ni down, and then experiment tells you that T is of the order of 0.4 electron volt and U is of the order of 4 electron volts. So this may vary depending on sample to sample, but it's of the order of, so we can see that roughly it's of the order of 10. So that means, so this U will be only there when there is more than 1 electron per site. So it's having a double occupancy is energetically costly. Okay, so we can construct a low energy effective Hamiltonian by applying simply the second order degenerate perturbation theory, and at half filling we can write the effective Hamiltonian is given by the Heisenberg Hamiltonian, where J is given by 4T square by U. Okay, and from there we can also know that the ground state is given by the nil state. Now what will happen is, basically because we are at half filling, so we have every 1 electron per site, and since double occupancy is energetically costly, so electrons cannot move, so that's why it's an insulator. On the other hand, charge degrees of freedom can fluctuate due to the second order processes. Now what will happen if we use the doping in the material? It happens is that we have removed some of the electron from the lattice side, so that's why now electrons can move. So it can be given by this TJ Hamiltonian, where we have the next term, which is Si dot Sj, the Heisenberg term, and now we have the hopping term, but we have two projections operator acting on both sides, just to make sure that there is no double occupancy, because it's energetically costly. So here this Pi operator, so this projection operator P, they just say that so no double occupancy is allowed. Now to develop a theoretical method, we start from we think that a good starting point is extreme correlation. We take U is equal to infinity. So J is of the order of T square over U. So if I take the U is equal to infinity, J term goes to 0. So we have only this projected hopping Hamiltonian, where we have, it's a standard hop, so it's basically hopping and it's projected by both sides. Okay, so although we can see that it's just a simple hopping, it's just a hopping Hamiltonian, but it's not a free fermionic Hamiltonian, because we can see that there are 4 fermion and 6 fermion terms present in the Hamiltonian. So it's a strongly interacting system. So, and if we just expand this hopping term, we can see that it has 3 kinds of terms. First term is the conventional bare hopping term. Second term is basically, second and third term are basically hopping coupled to the density fluctuations, and fourth term is basically hopping coupled to 2 density fluctuations. And I want to find the solution for this kind of Hamiltonian, where you can see that every term is of the order of T. So we cannot apply the standard perturbation theory. Okay, every term has, so basically even if we have a conventional hopping term, which we can act as an H0 or free part of the Hamiltonian, but our interaction is of the same state as the free Hamiltonian. Okay, so we have to develop a technique to find approximate solution for this Hamiltonian. So it's not that we are the first one who have solved this. This Hamiltonian has been studied in the literature, mostly in terms of in the language of Hubbard X operator. X operators are special kinds of operator which basically changes the state from beta to alpha. So now usually in terms of X operator, this hopping Hamiltonian, we can write it formally in the language of like a hopping term. But we can see that still it's an interacting Hamiltonian. So these X operators can act as a Bose and Fermi operator depending on whether they change the local electron by 0 and 1. So they follow non-canonical commutation and anti-commutation relation, which is given by this. So one of the good reference for this is basically this first paper, this book by Ovchinnikov and Volkov. Now using this X operator, there is a whole theory of extremely correlated Fermi liquid was developed by B. Sriram Sastry, and these are the reference to study this kind of Hamiltonian. And I will come to his result later. And then there is work done by Hassan et al. And then this is the semi-analytical method that we use our results are same as in this paper, but since we have done the whole calculation in the canonical fermion language, so we can know what are the relevant scattering processes. And second thing is that this Hamiltonian has recently been explored by functional renormalization group method by Peter Kopier's group, and this is one of the reference. And finally, there is in one dimension, there is a recent work done on the exact solution where they have used the Bethe answers technique. Okay. So we don't follow this any of this. So we just start with the projected Hamiltonian. We have added a chemical potential term just to work in the grand canonical ensemble. So we use the vintage this Jubarev double time temperature Green's function formalism. So here this is the definition of the Jubarev Green's function. So here the plus sign denote that it's an anti-commutator, and then the expectation value with respect to it's basically thermal expectation value. And then we use the Jubarev notation. This double bracket indicate that it's basically anti-commutator, and then we have to take the expectation value with respect to partition function. So we start with since we are mostly interested in the transport properties, so we just start with the Heisenberg equation of motion. So first term is usually just normal term. We are interested, so because we can compute the transport properties from this Jubarev Green's function, so we just write the equation of motion. So for this equation of motion of this this Jubarev Green's function, we take the derivative with respect to t. So that's why first term is simple, but in the second term, this commutator with the Hamiltonian, it will create a plethora of terms. So some of them can give you back this Jubarev Green's function, but then other terms will not. It will create a new kinds of Green's function. Okay, so now if you want to know what is this new kinds of Green's function, you have to construct the equation of motion of this new kinds of Green's function, and then it will again generate again a new kind of more new kind of Green's function, and then this hierarchy will continue. So usually in case of, but this is also true for in the standard field theory, but in standard field theory, due to the small parameter, we can truncate the series up to some order, but here we cannot truncate because we don't have a small parameter. So that's why we just use the formalism which is given by this irreducible Green's function method. So what we do is basically we have written this commutator as a sum of two terms. So first term is basically mean field term. Why is this mean field term? Because this all the elements in the E, they are basically mean field values. On the other hand, this the whatever is left, this Z, these are called the fluctuations. Okay, so now we can see that we have, although we can exactly commute this, we can exactly find this commutator, and although we can write it as a sum of these two terms, this decomposition is not unique. Okay, so because I can just take any term from the first term and then I can add it to the second term, it will not change anything. So I use the approximation. So now I use the first approximation, which is called Mori-Johanjig orthogonality condition. So I assume that, so it's basically the mathematical form of the approximation is this. Physically, this means that your fluctuation is orthogonal to your mean field value. Okay, so now if you use this condition, it will do three things. First thing, it will uniquely decompose it will uniquely decompose this term. So that means it will fix this E term and then Z term. So it will fix what is your E and what is your fluctuation Z. And once you have this E and Z, you can put it this. So due to this condition, some of the terms will become zero. So you can put whatever is remaining in the commutator to this equation of motion, and then you can go to the Fourier space. In the Fourier space, you can write the equation of motion in this form. The second thing you can get is that, so because of this condition, you can get a generalized mean field. Okay, so this mean field, we can see that. So you can so this mean field is like a free fermionic mean field. So here this Q1, but it is modified by two EQs, Q1 and EQ2. These are some mean field values, but you can see that TQ2 is usual normal term. We can absorb is in the mu, but this Q1, it actually modifies the dispersion relation. So basically this in case of square lattice, so this dispersion relation will be some 2t cos k, but it is now multiplied by the factor of Q1. So earlier what was the bandwidth 2t, so it is now reduced by Q1 times 2t, and Q1 is 1 minus n by 2. So it relates with the density. So now, and the third thing it has done is basically it closes the infinite hierarchy of the Green's function in a such way that, so we have seen that in case whenever we compute the equation of motion for the Jubarev Green's function, it has generated a new kind of Green's function which we'll call it as irreducible part of the Green's function. So now if I just write the equation of motion for the irreducible part of the Green's function, we can write it in this way. So it's a t which t times some g mean field. So where this g mean field part is basically what we have got from this equation, first equation. And now if I put this 19 in the 17, we can write it in the Dyson form. So this becomes a Dyson equation. So because of this condition, we have started with Heisenberg equation of motion, and this condition converts the equation of motion to the Dyson form. Now once I have Dyson equation, I can find that this is my just like a scattering matrix or scattering term, and from there we can construct the what is my self energy. Okay, so and remember that under this condition, this scattering matrix is exact. Okay, so we can exactly know what is my scattering matrix. So from the scattering matrix, I can construct the self energy, and this self energy contains higher order correlators. But we can see that we can exactly compute this self energy. Okay, now once I know the self energy, we can go to the we can see that this contains higher order correlator, so we have to simplify it. So what we can do is basically, and then this is a new method, so we have to benchmark our result, whatever result we are getting, because since it's a non-perturbative method, whatever results we are getting, we have to benchmark it. So we go to d is equal to infinity limit because it will simplify the self energy. And second thing is that we have used the Weeks decoupling to simplify this self energy further. And in the infinite dimension, we can see that this self energy is a sum of two terms. So first term is the Jubarev Green's function, but coupled with, but whenever we do the Weeks decoupling, we use this Weeks theorem to go to the two particle level, such that we write the self energy as a sum of susceptibility times Green's function in such that when I will use the self consistency, it will automatically modify the self energy. So now now I go to d is equal to infinity limit. So d is, and we can see that the self energy contains susceptibility, which are basically is spin and charge correlation functions. Okay, so we can go to the infinite dimension, and then we just add more theory, so more simplify that. We want to solve this only for the paramagnetic metallic phase. Since we are interested in the strange metal phase, we just want to solve this for the paramagnetic metallic phase. So in that phase, the spin and charge correlation functions are same, they are just differed by a factor of 2. So they are basically same thing, and then these are fluctuations that can act as a boson. Okay, so these are coupled to this Green's function. So this this fermionic Green's function, and the second term is basically sigma 2. So here we can see that one kind of bosonic fluctuations is attached to the fermionic Green's function, but in the second term, sigma 2 term, we can see that two kinds of bosonic fluctuations are attached to this fermionic Green's function. So now once we have this term, we can draw the diagram where this is the relevant scattering process. So first term is basically single boson term where the electron scatters with these bosonic charge fluctuations, and the second term is basically bosonic term which scatters with two types of charge and spin fluctuations. Now once I have this kind of diagram, we can just, now we have to compute, but still we don't know what is this charge and spin correlation function. So we again use the equation of motion to convert this equation convert this spin and charge correlation function to the current correlation function, and we can see that these bosonic fluctuation modes, they are basically massless modes, and and then we have converted everything to the current correlation functions, and then we can write everything in the spectral function representation, and then we can compute using the Matsubara formalism. Okay, so we can compute, and then we are solving it using self-consistently. so we have this charge and spin correlation function. So we have these charge and spin sectors, and then we can uh, compute both of them from the particle hole bubble. Okay, so this is basically the density correlation function, and since we are in a paramagnetic metal phase, both of them are same, so we can compute the charge and spin sector both from this particle hole bubble. Now once we know this, so we can see that these are fermionic spectral function which is appearing, so we can solve it self-consistently. So we start with some initial guess value of some doping, hopping strength, and then density of state. So we have used we are working this calculation at d is equal to infinity, so we have used the Bethel lattice for the numerical computations, and then we have started with some initial guess value of the self energy. So with the initial guess value of the self energy, so we can construct the interacting Green's function. So using that interacting Green's function, using this formalism, we can compute all the susceptibilities, and once I know that charge and spin susceptibilities, from there I can construct the bosonic propagators, and once I know the bosonic propagator, from there we can compute the self energy sigma 1 and sigma 2 both. Our total self energy is basically sum of these two terms, sigma 1 and sigma 2, and once I can compute this total self energy, I can check that whether it has converged or not. Okay, yes.
You have 5 minutes.
5 minutes. Okay. So basically, I'm fine. Okay. So basically, and then we can compute again the Green's function, and we can check that, and and after convergence, we can compute the observable quantities. So this is the first thing. This is the bosonic spectral functions. We can see that. So these are not sharp mode. So these are bosonic spectral functions. These are not sharp mode, and we can see that. So it's not. We cannot map it to the. So it's basically it's damped. It's also damped mode because it's not going to zero. So you cannot map it with a delta function. And then from there, this bosonic modes, actually this charge and spin fluctuation bosonic modes, they basically couple to the electronic degrees of freedom, and they basically modify the electron dynamics. So this is the reason and these are incoherent modes. So this is the reason this giving to the T-linear resistivity in the strange metal phase. So we can compute what is average energy of this boson, so which is basically a kind of moment calculation, and I want to find what is the highest weightage in this bosonic spectral function at which frequency. So we compute that, and then we can see that. So this is basically that average energy of this bosonic mode. So this is basically KVT, and then this straight line. So and then we can see that below certain temperature, these bosonic modes are important. And then I have also, after the convergence is achieved, we can see that the total self energy has two contributions. Even in this bosonic, average energy has two contributions. One is coming from sigma 1 and another one is the sigma 2. Sigma 1 is basically one boson process, and sigma 2 is basically two boson process. And then we can see that below certain energy, these two are important. And then below certain temperature, I can see that this two boson process also becomes dominant over single boson process. After that, we don't know because we don't have the numerical accuracy beyond that temperature. So now this is the fermionic spectral function. So in the fermionic spectral function, we can see that this is an asymmetric behavior, and then this is not a delta function behavior. But if I lower the temperature a little bit, we can see that a Drude-like peak appear at zero frequency. And we can see that to understand the amount of this, so how many terms are there in this fermionic spectral function, I have just taken the derivative, and we can see that there are two most important factors contributing to this fermionic spectral function. And this I have computed this derivative for different doping, and then I have also computed the quasi-particle residue. This quasi-particle residue is almost like a constant, but is decreasing very slowly with the doping. So if I reduce the doping, so this residue actually decreases. The next thing is I have plotted is basically electron self energy. We can see that at low temperature, so basically this self energy becomes zero at zero frequency. So and we can see that, so these are two different temperatures. This is the lowest temperature. We can see that lowest temperature, in the self energy, the contribution from sigma 2 is increased. Okay, so this blue dotted line is basically contribution coming from the sigma 2. So two boson process becomes important at certain low energy. And then we have computed for different temperature and for the different doping. We can see that this mode exists, and this is there. And the next thing, the last thing we have plotted is basically resistivity. So it shows the linear resistivity with temperature, but with two different slopes. And at extreme low temperature, we can see that it can fit with a quadratic. So it gives some t-square behavior at extremely low temperature, which gives you the Fermi liquid-like behavior. And depending on that, we can draw a phase diagram with temperature with the doping. We can see that at extremely low temperature, there is a Fermi liquid-like behavior. And then above that, we have two incoherent regime. One is in which both of these single boson and two boson process are dominant, and there is an incoherent two regime where only the single boson process is dominant. Okay, so and then there is a classical regime, and then this. Okay, so I just need 1 minute. So basically, this matches with the proposed phase diagram given by this B. Sriram Sastry. And the final result is that to benchmark our calculation, I have compared it with the exact numerical result. So this is the DMFT result, which is quite qualitatively same as the result we have reproduced, we got. So this is not at u is equal to infinity, this is at finite u. But this result is a DMFT energy calculation at u is equal to infinity, and this is given in this paper. So this matches qualitatively well with our results. And recently there are some experimental observations in which this dispersion in high resolution RPS data, these two modes are observed. We still can't say about anything because we have not done the calculation for finite momenta. But so these two boson process and single boson process may be relevant in this signature. So with that, let me just conclude. So we have developed a semi-analytical formalism in terms of canonical fermion language, which basically reproduce the exact DMFT results. And then we have identified the self-generated single and two boson scattering processes, and then we are just planning to do it in d is equal to 2. And we can so basically we don't have any super exchange terms, so we just want to include this. And thank you for your attention.
Thank you for the talk. We can come now the questions.
So particularly your strange metallic phase, so compared to the Fermi liquid, that is the imaginary part of the self-inner, that should be omega square. But what type of scaling your strange metallic phase is scaling?
Are you asking about optical conductivity? So I have only seen the DC resistivity. Yeah. It's not quadratic, so in that sense.
Definitely, but I'm asking the number. Is it
number we have not computed. We have not actually. We have the data, but we have not yet computed the optical conductivity results because we want to do it in a 2D. So we are focusing on that. We have not done it. So it's not quadratic. So
definitely that's not quadratic, but that is a robust proof that is a non-formal.
Optical conductivity. Yes.
So that should okay.
We are planning to do it actually. So.
What is the momentum dependence of your bosonic modes?
We have not done. We have done it at d is equal to infinity.
Okay, so basically you're always in the strong clock regime. Meaning that you're not really conserving momentum.
So not really. So we are in. We had just done this calculation it at d is equal to infinity limit, in the DMFT limit.
So in that limit, what is the momentum dependence? There is no momentum dependence.
So we have not done in at finite lattice. So how I cannot say anything about. So in our computation.
This wavy line. What is the Q dependence of the wavy line? That's all I'm asking.
Oh, okay. So we have not done this calculation. So this is a formal way of just writing this. We have not done just computed this in a finite lattice size. We have done it computed in a d equal to infinity limit.
So it's momentum independent. That wavy line is momentum independent.
It's frequency dependent. This Q is frequency.
Q is momentum.
So Q is momentum. Yes. So basically, it's but we have not done this calculation. So just that to the diagram. We are planning to do it in 2D.
In your calculation, what is the momentum Q dependence of the wavy line? That's all I'm asking.
So I have not done the calculation. So that's what I am saying. So it's basically just the plotted. I have just plotted just to show this in a systematic way. So this term I am just plotted in, just to draw a diagram like.
The answer is there is no Q dependence.
Yes.
In your approximation.
in an app.
Okay, so we are running short of time. Let's thank the speaker once more for his talk.